From yesterday, let me recall a couple of things. So a type A arrangement in RP2 is, first of all, a collection of points, and then you draw all the connecting lines. So connecting lines are those which include at least 2 points. And then a line is called ordinary if it contains exactly 2 points. And Sylvester's question asked whether there always exists an ordinary line if not all points are collinear. And the answer is yes. So that's Sylvester-Galai theorem, which we talked about yesterday. And furthermore, we had Melchior's inequality, which told us that there are at least 3 ordinary lines, not just 1. So let me rewrite Melchior's equation. It was something like T2 equals 3 plus some k minus 3 times tk plus some s minus 3 times ms. And let me recall the terms in this equation. So tk, including this t2, is the number of k lines in this picture. But in order to talk about this equality, we pass to the dual picture. So the dual is a type B arrangement in RP2, where lines become points and points become lines. So in the type B picture, tk would be the number of points where k lines pass. And ms is the number of s-gons in the polyhedral subdivision of RP2 formed by the lines in the type B arrangement. And in particular, since these two sums in this equality are always non-negative, all the terms here are non-negative, this tells you that T2 is at least 3. And a natural next question is to try to say something about T2 in terms of the number of points in the type A arrangement, or number of lines in the type B arrangement. So the question is, new question of today. If we start with n points in the type A arrangement, what can we say about T2 in terms of n? Sometimes the minimal possible T2 is sometimes denoted by m of n. If I use this notation, that will mean among all such arrangements, what is the minimal possible value of T2? Now, intuitively, of course, once one has more and more points, one expects that there should be more and more ordinary lines. I mean, more ordinary lines should be kind of forced by the situation. But okay, so far we just have that it is at least 3. And so how can we improve this? Now, the Dirac-Motzkin conjecture from 1950s makes a rather precise prediction. It says, except for 2 special configurations, special arrangements, which I'll describe, which occur for n equals 7 and n equals 13, these 2 specific numbers, one always has m of n greater than or equal to n over 2. So this is the conjecture. And in this generality, it is open. It's not settled yet, although there, as we'll see, there is lots of progress. Another remark is that this is not exactly the way it was stated first, so this is historically not precise, but I mean, eventually it took this form. Okay, now let me say a few words about these special examples for n equals 7 and n equals 13. So the one for n equals 7 is quite easy to draw. It's maybe one of the first things you would try. So I'm drawing the type A picture. So there are 7 points to start with. I'll choose them to be the vertices, the midpoints of edges of a triangle, and also the centroid. So these 3 lines would go through the same point. These are the 7 points. Okay, but we should be careful. I didn't yet draw all the possible connecting lines. There are 3 more which I should draw, and there are those 3. Now all the connecting lines are on the board. So in this picture, n is 7, and T2 is 3. It's these 3 yellow lines. By the way, all the other lines are 3 lines. They have 3 points each. And how many of them are there? There's 1, 2, 3, 4, 5, 6. So T3 is 6 in this picture. So of course, 3 is less than 7 over 2. So this, in a sense, doesn't obey this inequality, mn greater than or equal to n over 2. But as I mentioned, this was one of the exceptions. Okay. The second example is a little bit harder to draw, so I'll try to show it on the screen. So let's see. I think it should be visible now. Now, one thing about this is, okay, in this example, n is equal to 13, but it's a little bit deceptive. By the way, this is from the paper of Sima and Sawyer. This is a little bit deceptive because this is the type B picture. That means instead of 13 points, you have 13 lines. So already on this figure, you see 12 lines there. So if you count them, there should be 12 of them. The 13th line is the line at infinity of RP2. Okay, so these are the 13 lines. So where are the, okay, this is a type B picture, so I should count the ordinary points. Ordinary points are those where only two lines intersect. So you'll see one right here on top, there's 1 point, and symmetrically there's one here, that makes 2. There are 2 ordinary points in the middle, 3 and 4. Well, the other 2 ordinary points are at infinity. So to see which ones, okay, remember that parallel lines in R2 would intersect the same point at infinity. So for example, these 3 vertical lines all go through the same point at infinity, so that's not an ordinary point. Also, taking into account the line at infinity itself, that's a 4-tuple intersection. Likewise, there are 2 slanted lines which are parallel. They would intersect the line at infinity, so that would be a triple intersection. But there are 2 lines, these ones with the least slope and this negative slope, this go from this corner to corner, which have no parallels. So those 2 lines intersect the line at infinity and create ordinary intersections. So that contributes to T2. The total value of T2 here in this picture is 6. So let me write that here. So in this Mackey configuration, you have n equals 13 and T2 equals 6. Again, 6 is a little bit lower than n over 2, so it doesn't obey this inequality. And to this day, these are the only 2 known examples of line arrangements which for which Mn is strictly less than n over 2. And the conjecture is that these are the only 2. Okay, now there's another good reason why this conjecture says exactly n over 2 here, because there's an infinite family of examples where n over 2 is exactly gotten. So let me say something about those examples. Okay, these are the Bursky examples. So this is a class of examples for which T2 is equal to n over 2. And obviously for this to happen, n must be even. Okay. Now, okay, how to construct these examples? Okay, you have to choose 2 k points and draw all the connecting lines. Now choose k of the points as vertices of a regular k-gon. So This is how we start. Well, I have to choose k other points to complete it to k. And those other k points will be chosen to be certain points at infinity. So let me try to draw the example for, let's say, k equals 6. So you start with a regular hexagon. And somewhere far away, there's this line at infinity. Okay, I'm allowed to put 6 other points, and I'll choose their places carefully. I'll try to reduce T2 as much as I can. Now, okay, for such 2 parallel lines, I want them to intersect at the same point. So remember that every direction of parallel lines shows you a point at infinity. So I can do that. Then there are exactly 6 ways to rotate this picture and capture all the diagonals. So, for example, for this pair of diagonals, there should be some other point at infinity. I'll get that one. What else? You can also do things like this. Now, this time, these 3 parallel lines meet at a certain point, and so forth. In this way, you'll get 6 points at infinity, one corresponding to each of these parallel directions of diagonals. Okay, then you have lots of triple or quadruple intersections or something like that at infinity. Where are the ordinary lines, you may ask? So are there any ordinary lines in this picture? Of course, that must be because of Sylvester-Gallai theorem. Now, the thing is, once you choose this parallel direction here, these 2 points at the 2 ends, there are also lines, parallel lines to those diagonals, which go through this point at infinity, but which don't contain any other vertex. So, I mean, I start here, it's just kind of tangential to this hexagon, and at infinity it goes through the same point. Okay, this gives you this is an ordinary line. This green one is an ordinary line. And likewise, you have one here. Actually, every vertex of this hexagon lies on exactly one ordinary line, because only once it is alone on a line which goes to one of these points at infinity. So you obtain exactly k ordinary lines. So T2 is k, which is exactly n/2 in this example. This works for all even values of n. It doesn't work for odd values of n. And there's a good reason, actually. It turns out such examples don't exist for odd n. The best you can do is, as we'll see a little bit later, what you can do is around 3n/4 rather than n/2. So in other words, at least asymptotically, Dirac-Motzkin bound is sharp for even n, for large n, and for odd values of n, the correct bound should be around 3n/4, at least asymptotically. We know these from results of Green and Tau. Now, okay, these were some examples. Now, how to get bounds? Now let's start from Moser's theorem. Okay, this theorem says if the number of points is even, then this number m of n is at least, or strictly greater than, so to say, m plus 11 over 6. So this is yet far from n over 2, you might say, but still it is substantial because now you have some bound which increases with n. Okay, the proof is elementary. It uses this Melchior inequality. Okay, so I'll assume we're in a type A arrangement. Okay, so a K line is a line containing K points. That's the terminology. Now, you count the pairs PL point and line pairs such that P is on L and L is a K line with K not equal to 3. So somehow try to exclude the 3 lines and for all the other lines count pairs of points lines. Now the number of K lines is Tk. So this number, whatever it is bounded above by the following quantity. Let's call this number n. Well, for 2 lines, for ordinary lines, we have 2 points on them. For the 4 lines, we have 4 points on them, and this goes on like this. Even if none of these points are common, none of them are counted twice, this is as much as you could get. Okay. Now, let's write an obvious inequality. Instead of this coefficients 4, 5, 6, I increase them. This is true because now the coefficients are 4, 8, 12, and so on. They're substantially increased. The only reason for doing this is what we see in Melchior's inequality. So this is 2t2 plus 4 times sum k minus 3 times tk. But now this sum did appear in Melchior's inequality. Okay, this is bounded above by t2 minus 3. Remember, T2 was equal to 3 plus the sum plus something else. Okay, so this is 6T2 minus 12. So what does this say? I mean, the moral of this is actually, I mean, you can see this as a trick, but the moral is the following. Melchior's equality says, if t is small, then all of t4, t5, t6, etc. must be small as well. Okay, so t3 must carry the burden. Okay, now let's come to the proof. So if t2 is less than or equal to this bound, we want to get a contradiction. This would say n is less than or equal to 6 times this number minus 12, so n minus 1. 1 less than the total number of points, so there exists a point which lies only on 3 lines. That would be the corollary. But let's now show that this will produce a contradiction. So suppose there is such a point which lies only on 3 lines. Then, okay, the picture would be like this. You have some P, you have lots of 3 lines, which means each of them contains exactly 3 points. This maybe, so forth. And all the points are here, right? Because you have to draw all the connecting lines, so all the points must be connected to P. So all the points are around. But then this would imply that the number of points is 2 times the number of such lines plus 1. So it is odd, contradicting the assumption that n is even. So there's an even-odd game, and this gives you the contradiction. This is very nice, only it uses an even-odd trick, and it's maybe unclear if it has something to do with parity. Well, we'll see that I mean, there are other results which don't mention even parity, and we still are bound, but this is a good start. Okay, now for the upcoming results, let's make some definitions. Okay, again, we start from some PL, a type A arrangement. Inside RP2. And P a point in this point set. Now, if you look at all lines which do not contain P, they will subdivide RP2 in some way. So the lines in L not containing P subdivide RP2. Okay, so the picture is here is P somewhere. You don't draw the lines through P, let's say. Just draw the lines which are through the other points, like these, whatever. Now, the region that P lies in will be called the residence of P. And the lines which go around this residence will be called neighbors of P. Lines bordering the residence would be called neighbors of P. Some natural definitions, I suppose. And also, we want to make a count of the ordinary lines going through P and also the number of ordinary lines among the neighbors. So we'll give these names. So definition. The order of P will be the number of ordinary lines going through P. So these contain P and one other point. Well, of course, this number might be 0 for a particular point. That's possible. The rank of P will be the number of neighbors of P, which are ordinary lines. And finally, the index of P will be the sum of these two numbers. So index So you have these three numbers defined for all points of P. And we want to say some things about these numbers. Okay. For example, let me state and prove a lemma regarding these numbers. It says, if the order of P is 0, then all the neighbors are ordinary lines. Okay, so if no ordinary lines pass through P, then all the neighbors must be ordinary, it says. So this is an important step for what's coming up. So let's prove it. So we have P here, which is assumed to be order 0. And you have a bunch of neighbors like this. Now the proof will use Steinberg's proof of Sylvester-Gallai theorem. Actually, it will use the idea, not the proof itself. So select a neighbor. For example, let's look at this one. I want to show that it is ordinary. Suppose not. If it is not ordinary, that means there are at least 3 points on it from the point set. Maybe they don't have to be right on this edge. They could be somewhere here, here, and here maybe. Let's say these are, I don't know, P1, P2, P3. Okay, what's wrong about this picture? Nothing yet so far. Now you pick some point on this edge, which is on the neighbor, but also on the edge. So okay, let's call this point X. Of course, this usually will not be in the point set, but it's an auxiliary point. Okay, now if you look at this 4-tuple P1, X, P2, P3, okay, again, you have 4 points on a line. The orders might be quite different, but always 2 of them will separate the other 2. For example, in this picture, P1 and P2 separates the other 2, X and P3. These, remember, this projective line is like a circle, so it goes around. But if you have 4 points, 2 of them separate the other 2. Okay, so this P3 is the other one of the pair together with X. So draw this line, connecting line, P3, P. It cannot be ordinary because the order of P is 0. P3, P is not ordinary. Since order of P is 0. Therefore, it must contain one more point somewhere, P4, let's say. But now, depending on where P4 is, you can always produce another connecting line. For example, here, P2, P4. Which intersects this segment, Px. But that's bad because now X is, I mean, this segment is not a neighbor of P anymore, right? So X was supposed to be on this neighboring segment, but there's another connecting line which kind of cuts through the 2 and makes the region smaller. That's a contradiction. If P4 is somewhere else, then it might be the other point which works. So for example, if P4 is rather here, then you don't use P2, but use P1. Use it this way. Again, it cuts the segment. For every placement of P4, one of these points will give you some connecting line subdividing Px, and which creates a contradiction. And that finishes the proof. That neighboring line must be ordinary. Okay, this is an important thing that we'll use. Let's prove another lemma, which is actually a little bit easier. Okay, now consider the section of RP2. Into polygonal regions by the ordinary lines of the arrangement. Okay, then you have some bunch of ordinary lines, and you have some regions formed. The statement is that each region can contain at most one point in its interior. Let me stress that these are the ordinary lines only, so you don't draw all the lines, it's just the ordinary lines. Okay, the proof is this time easier. Okay, let me just do it by drawing. Here's an ordinary line. Here are potential 2 points in this region. Okay, then what you do is again like Steinberg's proof. So okay, I'll just be sketchy. So you can shrink the residence of P shorter by doing this thing. But again, you have to repeat this proof. Maybe I was a bit hasty to say it's too quick, but again, you repeat the Steinberg's argument to even shrink the residence further. So, okay. Now, putting together these results, we can get our next bound. This is the results of Motzkin. It says this Mn is greater than square root of 2n minus 2. Okay, this is a lower bound for every n, odd or even, it doesn't matter. So that's good. It's quite far from this linear bound n over 2. It's just square root of n, so that's not very good. But still, it tells you some lower bound for every n. So, okay, so how do you prove this? We just put together what we have done. So consider the dissection of RP2 into polygonal regions by using this Mn ordinary lines. Now the number of regions is less than or equal to, well, how many regions can Mn lines subdivide RP2 into? So this is at most Mn choose 2 plus 1. This is the maximal number of regions that you can obtain. Now, we saw, let's put together the last two lemmas. Now, points of order 0, these must be contained in such neighborhoods. There are contained in interiors. Because all of their neighbors are ordinary, we prove that. And furthermore, each region can contain at most one point. Now let's write our estimate. Now, there are at least n minus 2 Mn points of order 0, because these Mn ordinary lines can contain at most 2 Mn points, and anything other than that must be of order 0. But each of these order 0 points is contained in a separate region. Therefore, this must be less than or equal to the number of regions. Now, this Mn choose 2, let's write an obvious inequality. This is less than, well, we can calculate this thing. Maybe I should do it over here. Okay, then n is less than or equal to 2Mn plus Mn times Mn minus 1 over 2 plus 1. So this quantity is Mn squared. This is minus Mn plus 4 plus 3 Mn and plus 2, if you like, over 2. We can say this is less than or equal to Mn plus 2 parenthesis square over 2, because this would only increase this coefficient 3 to 4 and this 2 to 4. That's an obvious inequality. Actually, this is strict. And this implies that's Mn plus 2 square is greater than 2n, and I believe this is what we wanted. Which is what this theorem stated. Okay, so this was Motzkin result. Well, all of this is very good. We have some nice bounds, but still this is far away from the conjecture, which is n over 2. The next result, which is due to Kelly and Moser, is a substantial upgrade. It will tell you that Mn is at least 3n over 7. Okay, maybe before going into that, we might take a break. Okay, let's start the second part of today. So the next result is the theorem of Kelly and Moser. This is from 1958 already. So they say for a type A arrangement, with endpoints not all points collinear, we have m of n is at least 3n over 7, which is substantially better than all the results that we have proven so far in this lecture. So, and 3n over 7 in a sense, because there's the special example for n equals 7 with 3 ordinary lines, so equality is satisfied there. Okay. So let me try to do an outline of proof. I think we can more or less do the whole proof, maybe leave a couple of easy details as exercises. First, let's handle a special case, which is near pencils. So it's good to get rid of this special example. So a near pencil is where you have a point and all other points on a single line. So in this case, T2 is equal to, okay, the number of ordinary lines is n minus 1, which is far greater than 3n over 7. So the condition is satisfied. So what is special for what we'll do is, in a near pencil, this apex point has just a single neighbor, it's this line. And all the other points have 2 neighbors. So this point would have this line on the left and the one on the right as neighbors and no others. So points here have 1 or 2 neighbors. And it's an easy exercise, which I'll leave for verification. If in an arrangement a point has 1 or 2 neighbors, any point, then it must be a near pencil. Then the arrangement is a near pencil. So, but for near pencils, this bound is satisfied, so we can discard this case, and so we don't have to deal with the case of points having 1 or 2 neighbors. So from now on, we can assume that it's not a near pencil, and every point has at least 3 neighbors. From now on, assume the arrangement is not a near pencil. So all points have at least 3 neighbors. Okay. Now let's go on. The following lemma is an important step. It says if a point has order different from 2, then its index is at least 3. So remember, index was order plus rank. So the order 2 points might have index 2, but for all other points, the index is at least 3. Okay. Now, okay, we might assume every point has at least 3 neighbors, as I said. So now the first case, if order of p is 0, then we saw that all neighbors are ordinary. And there are at least 3 of them. Therefore, the index is at least 3. Okay, so this is taken care of by a previous lemma. Now, also the case of order greater than or equal to 3 is obvious, because index is at least as big as order, so nothing to talk about. So the only interesting case remaining is when order of p is 1. If order of p is equal to 2, we don't say anything anyway. Okay, so let's try to take care of the case order p equals 1. Okay, so then you have your point P and a single ordinary line which passes through this point. Of course, there are more connecting lines, but there's only one ordinary line. Okay, now this ordinary line should have one more point on it. Let's call it P1. The claim is if a neighbor of P is not ordinary, then it has to pass through P1. And how do you show that? So suppose not. Okay, suppose this is a neighbor. So let me draw something like this. Maybe here's a neighbor which is not ordinary and which doesn't pass through P1. So it must have at least 3 points on it. Okay, there might be some other neighbors here, and let's say this is the residence of P somehow. Okay, now choose 3 points on this line. It's assumed to be non-ordinary. Let's say these are P2, P3, and P4. So we'll do something similar to, again, the Steinberg's idea. So select a point on this boundary, let's say X, and look at the segment. Now this P2, P3, X, and P4, two of them will subdivide the other two. So in this picture, it's like P2X and P3, P4. Now draw the connecting line through P2 and P. Okay, now what's the problem? Again, it's the same argument as before. So this PP2 is not ordinary. Because by assumption, there was just one ordinary line through P, and that was PP1. So PP2 is not ordinary, so it must contain another point. Let's say Q. But depending on where Q is, either P3Q or P4Q creates a problem. It subdivides this interval, which says X is not in the boundary of the residence. So it is a very similar proof to this lemma saying that order 0 points have ordinary neighborhoods. Of course, this proof would break down if P2 is equal to P1, right? So I mean, if this line passed through P1, then this line PP1 would be ordinary, and you cannot go on. So this is why it has to go through P1. Okay, so this claim is correct. Now, let's see what that tells us. Now, this point P has at least 3 neighbors. And there's P1 here still. If 2 neighbors are ordinary, then nothing to talk about because order is 1 and 2 neighbors are ordinary. That makes index 3 and we're done. So what's the bad case? Well, you might have 2 non-ordinary neighbors which pass through P1 and an ordinary neighbor, maybe a triangle like that. So can this happen? These are non-ordinary, whereas this is ordinary, and this is the residence of P. So can we have this picture? We want to outrule this. Now, I claim that at least one more of these is ordinary. This picture cannot happen. Okay, so suppose, for example, I take 2 points here. Let's say P2, P3. Then what's the problem? Okay, again, select the point X here. Now, this line P3X is not ordinary because there was only one ordinary line through P, and that was PP1. So it must contain a third point, and it's again the same game. So if this Q is here, you join P2 with Q, then it shrinks the neighborhood and cuts X away from P, right? If Q is somewhere here, then you draw P1Q, and again, that cuts this thing, so this cannot happen either. It's the same proof over and over again. So this shows you that even in this case, there are at least two ordinary neighbors. So as a result, index of P is at least 3, and that finishes this lemma. Now, before we can finish the proof of Killing-Moser theorem, there's one more lemma to handle. Okay, this is rather general. It says a line in L in the arrangement can be a neighbor of at most 4 points in P. Okay, let's prove this. Okay, the first case to note is that 3 collinear points cannot have a common neighbor. L. I can almost show this by drawing a picture. So suppose you have 3 collinear points, and this line L, which is supposedly a neighbor of all these points. But remember, this must be a connecting line, so there must be some point on it somewhere. And that implies all these other lines should be connecting lines. But then these two lines cut away this one so that L is not a neighbor of this middle one anymore. Well, this is projective space, so this region goes back and comes back from here, but still, no segment of this line L is a neighbor of the residence of this point. Therefore, this cone cuts this middle point off from L. If the points are on different sides of L, nothing changes. So let me draw such a picture. Only it's a matter of which points cut off which point. So in this case, I have to draw, I suppose, these two connecting lines. So this was L. These two connecting lines keep away this point. So L is trapped in some cone, and this point is trapped in another cone, and so this point cannot be a neighborhood of L, in a neighbor of L. Okay, so this is done if the 3 points are collinear, and this argument also shows you that the only way to have 3 points all neighbor to L is if none of them lies in the cone that's produced by two others. So then this tells you that something must be special for all 3 points to be neighbor of the same line. So let's now pass to non-collinear case. So let's say P1, P2, P3. Suppose all of P1, P2, and P3 are neighbors of L. Then that means this point on L shouldn't produce a cone such that it cuts away any of the points. So the only possible places for the points are the intersections of the lines Pi, Pj with L. So this is a possible place. This is a possible place. So if I'm a little bit on the right, it doesn't work, right? So I'll produce such a cone, which will cut away P2. That's bad. But if I'm just on the border, both P2 and P3 could be neighbors of L without producing a contradiction. And the third place is, of course, the intersection of P1, P3 with L, which is maybe not very apparent in the figure. But so the only places for points of P on L are these intersections Pi, Pj intersect L. But then you see the upper bound. There must be at most 4 points because, simply because there are not enough places to put points. So that almost immediately implies this lemma. By the way, this 4 can be attained. So for example, if P1, P2, P3, P4 are here, let's draw a line which is neighbor to all 4. All you have to do is to draw these lines. Then, for example, if you select P and Q right here, then the line PQ is a neighbor of all 4 points. For example, P2 is a neighbor of L because this edge is a boundary of the residence. Likewise for P1, and this edge from Q downstairs is a boundary of the residence of P3 and P4 and so forth. So 4 points can be a common neighborhood of a line. Okay, now I guess we are quite ready to finish the proof. Here's one more small lemma, but this one is easy. Okay, so if I sub I denotes the index of points Pi, then the claim is Mn is at least 1/6 sum of the indices for over all points. Okay, the proof will follow by some double counting argument again. So this time count the pairs PL such that either L is ordinary and P is on L, or L is ordinary and P is L is a neighborhood of P. L is a neighbor of P. Well, you can count this from the perspective of the point or the line. So for a given PI, the contribution is to this double count is II, right? So I mean this index. It's the number of ordinary lines passing through P or a neighbor of P. So totally they give you the index. This contributes II. But then you can also count from the perspective of the line. Okay, now it's an ordinary line, right? So we are counting ordinary lines. So it contains at most actually 2 points. 2 points. And it can be a neighbor of at most 4 points by the previous lemma. So each line contributes at most 6. And it's only the ordinary lines which contribute, remember. So the total is less than or equal to 6 times Mn. But on the other hand, this is equal to sum of the indices. So this gives you the inequality. Now we can finish the proof of Kelly-Moser theorem. Okay. Now we have n points. Some of them may have order 2, the others don't. Okay. Suppose k of the n points have order 2. Then these have, of course, index at least 2. The others have index at least 3. So let's write the previous lemma in this fashion. So Mn should be greater than or equal to sum of all the indices over 6. So this k points have index at least 2. The other n minus k points have index at least 3. And now you have over 6. So this implies 6 times mn is at least equal to 3n minus k. Okay. Now, on the other hand, okay, what's an order 2 point? An order 2 point is a point through which there are 2 ordinary lines, right? So, and an ordinary line contains 2 points. Therefore, the number of ordinary lines must be at least as much as the order 2 points, because, you know, the more order 2 points you have, the more ordinary lines you have, and each line can be counted for at most 2 points because there are 2 points on it. So taking these two into account, add them up, you have 7mn, at least 3n, which gives you the theorem. Mn is at least 3n over 7. So that finishes the proof. Okay, so in a sense, this is an optimal result because there is an example with n equals 7 and t2 equals 3. But much later, in the 1990s, Sima and Sawyer proved this following theorem. So I'll just state this one. Again, suppose you have a type A arrangement with n points. Not all points collinear. And also not the special example with n equals 7. Then their conclusion is Mn is at least 6n over 13. So getting a little bit closer to n over 2. And of course, this is again optimal because there's this Mackey example for n equals 13 with 6 lines. Okay, I'll not attempt to prove this. It's a nice paper, but one has to do a little bit more detailed local analysis. And maybe a bit of history. In 1981, there was an announcement by Hansen which claimed the full Dirac-Motzkin conjecture, but it turned out to be incorrect. I mean, the proof had a gap. And in this paper of Sima and Sawyer, you can find what part is wrong. And also they used some of the correct results of Hansen to make this improvement. So they used this part of this result, but it wasn't strong enough to prove the whole conjecture, but it gave you this upgrade. Okay. Now, finally, I want to say something about this asymptotic version. So this is the result of Green and Tao. This is a more recent paper. It's in It's published in 2013. So they prove an asymptotic version of the conjecture. In particular, one of the results, there are many results in the paper, but one of them is the following theorem. Again, suppose you have type A arrangement. Endpoints, not all collinear. Okay. Then they say that there exists n0, some fixed number, fixed but large, such that for all n greater than or equal to this n0, we have T2 at least n over 2. So they get the Dirac-Motzkin bound, but assuming that n is greater than or equal to some large number. Now, there are many interesting techniques and ideas in this paper, so I'll not attempt to prove it. It's a long paper with lots of details. Maybe it would take a few lectures just to prove this result. But again, I can say something about the heuristics. So how they approach this problem. So you start from Melchior inequality. So T2 is equal to 3 plus the sum this is Melchior, right? Let's also write down something which is much easier. Now, you could try to make a double counting. For every pair of points, you have a connecting line, and the connecting line must be one of these k lines. If you do a double counting, you easily get the following equality, and choose 2 is equal to sum k choose 2 times tk. So this is an easy double count. Let me not give details. Okay, a particular consequence, if you look at these two together. So if T2 is small, say order n, so I use the big O notation to denote order. Okay. Now, several things happen at once. If T2 is small, then that means, first of all, T4, T5, all of these are small as well. Actually, not just them, but their sum is small. But I'll just try to do this heuristically. But then if all of these are small simultaneously, there is only one thing on which there is no restriction, that's T3. T3 is not in this equation. And moreover, you have an equality to satisfy, right? So, I mean, you have to add up some things and get something like n times n minus 1 over 2, which is of order n squared. So then you would expect that T3 is order n squared. So if T2 is small, then you expect a large T3. Lots of triples of points on lines. The triple here, another triple there. Some constant times n squared many. Okay. Then you have also one more piece of information coming from Melchior equality. That also means the second part of the sum is small. Which means the only term that doesn't appear here is s equals 3. So apart from triangles, these other larger polygons, quadrilaterals, pentagons, and so forth, you don't see them too much. So and most polygons in the subdivision are triangles. Then, using these two pieces of information, it is possible to prove that most of these points, if T2 is small, then most of the n points in a precise sense lie on a single cubic curve. Okay, but I mean, I said this, but the steps are tricky. I mean, first they prove that it must lie in a low number of cubic curves, like order constant many cubic curves. Then they have a upgraded argument to have a stronger structural theorem to reduce this number of cubic to eventually to 1. And there are quite many difficulties because at the outset there might be many irreducible components which are lines and so forth, and to reduce these number of lines to a low number takes lots of work. But once they do this, they just make a counting and use some additive combinatorics to get their result. So that's the outline of their proof. But as I said, there are quite many details, and one should spend some time to read all the details. Okay, so this might be a good point to stop for today.